Good morning. My name is Rosalia Tatano and I am a lead scientist in Ad4 Industriale. Also, on behalf of my co-authors, I would like to present our paper, Sanity Check for Shapley Value-Based Explanations of Deep Neural Networks Predictions. Deep neural networks, shortly DNNs, are algorithms trained to solve complex problems involving a large amount of data. When new data are supplied, a prediction is provided in output. However, the way DNNs reach a certain prediction is not easily understood. Thus, DNNs are named black boxes. The problem is that the user cannot trust a certain prediction given by a black box. In addition, if the working mechanism of the model is not fully understood, it is difficult to check if the model properly does what it is designed for. This is especially crucial in healthcare, where the outcome of these algorithms can have a profound impact on human life. In fact, the use of DNNs can be beneficial to clinicians to support decisions, optimize treatments, and uncover important information in the data. However, the trust of clinicians in these algorithms is compromised by the lack of transparency in the prediction. For this reason, in the last few years, there has been an increasing interest in explainable artificial intelligence, shortly XAI, that is the class of algorithms that could explain why a DNN reached a certain prediction. Thus, the objective of these algorithms is to provide an explanation of how the model works, which means the goal of these methods is to make the model interpretable. The use of explanation algorithms is particularly suited for DNNs applied in healthcare. The explanation, in fact, can help the clinicians to take better and reasoned decisions about the predictions instead of blindly trusting them. Following Montavon et al., we can define an explanation as a collection of features that contributed to the prediction. To have an explanation of the outcome of DNNs is useful for several reasons. The most important ones are social acceptance, safety, requirements of the law, and satisfaction of human curiosity. These are all evident in healthcare. Inside the XAI, in this work, we focus on additive features attribution methods. These are explanation methods where the prediction is decomposed as a weighted sum of the input features, with weights representing their importance towards the prediction. An important class of explanation methods is based on Shapley values from cooperative game theory. In a cooperative game, there is a set of n players, and their goal is to cooperate to achieve a common objective. The players can form coalitions. A function v associates to each coalition its worth, assuming that the worth of the empty coalition is 0. The Shapley values is a fair way to redistribute the total payoff arising from their cooperation, where the fairness is defined by a set of axioms. In the context of explanation of DNN's predictions, the players are the input features and the total payoff is the prediction. The goal is to attribute an importance score to all the features by means of the Shapley values. Lundberg et al. Proved that there is only one additive feature attribution method that satisfies the axiomatic definition of the Shapley values called SHAP, when defining V as the expected value of the model prediction given a set of fixed feature values. However, the numerical computation of the Shapley values is complicated because it requires an evaluation of V for each possible coalition. If the number of features is n, this means to make 2 to the n evaluations. These difficulties led to the introduction of approximation algorithms. In this paper, the focus is on Shapley sampling, kernel SHAP, deep SHAP, and DASP. Shapley samplings and kernel SHAP are two model-agnostic methods, which means they can be applied to several kinds of models. Instead, deep SHAP and DASP are two model-specific methods, specifically tailored to DNNs. Model-specific methods have the advantage of being computationally less demanding in terms of time and memory required for the computation than the model-agnostic ones, as they take advantage of the characteristics of the model they are built for. In the experiments, we trained an image classification network and calculated the explanations using the methods presented earlier. We want to perform a quantitative comparison of the computed explanations and to check if these explanations can be trusted using a sanity check. Similarly to a previous work, Shapley samplings is considered as a ground truth for the quantitative comparison. The considered metrics are the structural similarity index, shortly SSIM, and the normalized root mean squared error, shortly NRMSE. The similarity metric assesses the similarity between two images with a value of 1 indicating perfect similarities between the two images. The error metric measures the difference between the approximated values and the ground truth, and the lower its value, the better the agreement. In our results, the highest similarity with the ground truth is obtained by DASP, while kernel SHAP exhibits the lowest similarity score. This is confirmed by the values of the mean error. Deep SHAP obtained intermediate scores, and its maps are structurally more similar to those obtained by DASP than with those obtained by kernel SHAP. XAI algorithms pose an additional difficulty, that is the one of assessing the quality of the produced explanation. A sanity check of the explanation is then helpful, especially if applied in domains like healthcare. Indeed, if the explanations are not faithful to the model prediction, the medical user could be misled by the explanation itself. This work focuses on the sanity check proposed by Adebayo et al. That verifies that the provided explanations are dependent on the model parameters. If not, the method does not faithfully explain the model. The sanity check works this way. Given a trained model and an explanation, then all the model weights are randomly reinitialized in a cascading fashion, starting from the final network layer and all the way to the first hidden layer, completely destroying the learned weights. Explanations of the prediction obtained with the modified networks on the same input are calculated and compared to the original explanation. The similarity is quantified using the similarity index. If the score is close to 1, the XAI method fails the sanity check. The results obtained on the Shapley value-based explanation methods are compared with the two benchmark methods, namely gradient and guided backprop. The plot of the mean values and the standard deviations of the similarity metric for each step of the cascading is displayed in the figure. It is known in the literature that gradient passes the sanity check, while guided backprop does not. Shapley value-based explanation methods instead pass the cascading sanity check. In fact, the values of the similarity metric lowers for each Shapley value-based method as the learned weights are reinitialized. This is more evident for deep SHAP and kernel SHAP than it is for DASP. XAI methods are then useful to show if DNNs are robust and to improve the user trust. However, there is no guarantee that the explanation methods itself faithfully explains the model it is applied to, as we have seen. This can be misleading for the final user. Faithfulness to the model is important because the user should trust the DNN model, but it should trust also the explanation. Thus, it is important to develop XAI methods based on theoretical foundations, which should give also better theoretical guarantees of faithfulness, as for the Shapley values-based explanation methods. In conclusions, explainability is crucial for the application of DNNs to the fields that have an indirect impact on human life. Explanation methods offer a way to improve the user trust and the model safety. However, a good explanation method should be faithful to the model it wants to explain. Our results indicate that Shapley values-based explanation methods are a valuable tool to understand what a DNN considered important to reach its prediction due to their theoretical background. In the future, we plan to repeat the comparison made in this work on medical images data. Thank you to you all for your attention.